24 billion kilometers from our planet. A machine launched before the personal computer was invented is detecting a signal. A steady vibration coming from a region every scientific text declared was empty. We assumed we understood what existed out there. We did not. 8 separate times. The threshold was 2.1 billion kilometers nearer than our calculations suggested. The heat levels reached almost double what the laws of physics permitted. The protective envelope surrounding our sun carries no wake, no defined form, and a boundary that permits leakage. A 43-year-old reserve transmitter activated autonomously from interstellar territory, and a malfunctioning sensor that NASA nearly excluded from the spacecraft wound up validating the most significant transit in the annals of exploration. During the following 2 hours, we are going to track Voyager to the frontier and past it. If you find the voyage worthwhile, press like and subscribe. Now let us begin, because at this very moment, approximately 165 astronomical units from our world, Voyager 1 remains operational. Its plasma wave subsystem has been registering a continuous narrowband signal since 2017. A persistent tone in interstellar territory, roughly 0.04 kHz in bandwidth. Arising from a zone that every scientific framework characterized as void and hushed, the probe departed Earth on September 5, 1977. It was constructed to image Jupiter and Saturn. No engineer designed it to endure 48 years. Nobody anticipated it would still be relaying information from beyond the outer frontier of our solar system, a zone called the heliopause. Yet here it is. And the data it transmits requires approximately 22.5 hours to arrive at the Deep Space Network's receiver dishes. Another 22.5 hours for any reply to complete the return journey. A 45-hour round-trip exchange with an object 24 billion kilometers distant. The vibration is genuine. It reflects plasma oscillations in the interstellar medium. The tenuous gas occupying the void between star systems. Consider it like the faint resonance you detect when pressing your ear flush against a conch shell. Only the shell, in this case, is the galaxy itself, and the resonance is electrons pulsing at frequencies Voyager's 1.6 watts sensor can barely register. What renders this anomalous is not the vibration itself. It is what the vibration communicates about the space lying outside our solar system. The interstellar medium was expected to be frigid, undisturbed, and uniform. For generations, theoretical frameworks depicted it as an enormous expanse of near-nothingness, scattered hydrogen atoms adrift in blackness, precisely the kind of location where instruments would register nothing. Instead, Voyager revealed organization, variations in density, compression fronts, turbulence adhering to patterns that physicists associate with fluid behavior on Earth, patterns referred to as a Kolmogorov spectrum. The void between stars has its own meteorology, and the hum is merely one element of what our predictions failed to account for. Every significant threshold Voyager traversed was positioned incorrectly. Every reading at those thresholds invalidated the theoretical frameworks. The magnetic field was expected to shift orientation dramatically at the frontier. It scarcely budged. Particles that should have reached a maximum at one threshold continued climbing past it. The external temperature proved nearly double what anyone had calculated. 2 spacecraft traversed the same divide 6 years apart, and reported fundamentally contrasting phenomena. 8 distinct forecasts regarding the edge of our solar system proved incorrect. Not marginally. incorrect in ways that compelled entire branches of heliophysics to rebuild from scratch. The inquiry that follows concerns why our finest models of the space we inhabit failed so thoroughly, and what the actual measurements reveal about the bubble of charged matter that encircles our Sun and partitions us from the broader galaxy. That bubble bears the name heliosphere. We believed we had grasped it. We had not. And new evidence continues arriving, carried by a probe shedding 4 watts of generating capacity annually, decommissioning sensors one at a time, broadcasting on hardware assembled before the age of personal computing. The interstellar vibration persists. Voyager continues listening, but to comprehend what it discovered, we must revisit our assumptions from before any craft had ever neared the boundary. Before Voyager penetrated the outer reaches of our solar system, the heliosphere possessed a straightforward, well-established geometry. In every scientific reference, our Sun emits a perpetual outflow of charged particles called the solar wind. This outflow streams outward in all directions at velocities between 300 and 500 meters per second. At a certain distance, the outflow decelerates. It encounters the gas and particulate matter drifting through interstellar space, and the pressures equalize. That threshold was termed the termination shock. Past the termination shock, the solar wind was expected to slow still further and accumulate in a zone called the heliosheath. Envision water from a garden hose striking a flat surface. The water fans sideways upon impact, producing a turbulent layer before dispersing at the edges. The heliosheath represented that dispersing layer, and beyond it waited the heliopause, the ultimate threshold where solar origin matter concludes and interstellar matter commences. The heliopause was forecast to reside at approximately 150 astronomical units from our Sun. 1 astronomical unit equals the Earth-to-Sun separation, roughly 150 million kilometers. So 150 astronomical units translates to roughly 22 billion kilometers. The termination shock was anticipated at around 108 astronomical units, or roughly 16 billion kilometers. Beyond the heliopause, interstellar territory was modeled as frigid, sparse, gas at temperatures spanning 15,000 to 30,000 degrees Kelvin. That registers as extremely hot, yet the gas is so rarefied that actual thermal energy content is negligible. A handful of atoms per cubic centimeter, barely exchanging energy. Theoretical frameworks anticipated this gas would be structureless and silent. The geometry of the heliosphere represented established scientific consensus for 5 decades. Because our Sun navigates interstellar space at roughly 84,000 kilometers per hour, the heliosphere was expected to resemble a comet. A compressed, blunt, leading face pressed against the interstellar current, and an elongated wake trailing hundreds of astronomical units behind. Every diagram and every astronomy reference depicted this geometry. Every theoretical model computed it. Researchers constructed careers around the comet-tail heliosphere. The magnetic field represented another resolved inquiry. Our Sun's magnetic field spirals outward, carried by the solar wind, forming what physicists label the Parker spiral, named for Eugene Parker, who initially characterized it in 1958. At the heliopause, this spiraling solar magnetic field was predicted to collide with the interstellar magnetic field arriving from beyond. The collision would generate a dramatic reorientation of field direction. A compass needle, if you could suspend one at the heliopause, would whip sharply. That directional reversal represented the anticipated definitive signature for pinpointing the boundary. Anomalous cosmic rays contributed another prediction. These are particles that originate as neutral atoms drifting inward from interstellar space, become ionized through solar radiation, and subsequently accelerate to immense energies. The acceleration process was expected to function at the termination shock when a spacecraft traversed the shock front. Anomalous cosmic ray density should reach a maximum. Entire research initiatives were constructed around quantifying that maximum. This represented the framework. Termination shock at 108 astronomical units, heliopause at 150, a clean magnetic reversal at the boundary, a cosmic ray maximum at the shock, a long trailing wake, cold silence beyond. 50 years of theoretical development, all internally consistent, all mathematically coherent. The first fracture appeared on December 16, 2004, when Voyager 1 had been traveling for 27 years and occupied a position more remote from Earth than any human-constructed object previously. On December 16, 2004, Voyager 1's sensors registered an abrupt transition. Solar wind velocity dropped. Magnetic field intensity surged. Particle count altered. The spacecraft had traversed the termination shock, the threshold where the solar wind transitions from supersonic to subsonic velocity. This was the moment heliophysicists had anticipated for multiple decades. The recorded position was 94.01 astronomical units. The theoretical forecast was 108. Voyager encountered the boundary 2.1 billion kilometers nearer to our Sun than every model indicated it should be. To translate that separation into concrete terms, the forecasting error exceeded the gap between our Sun and Saturn. The entire theoretical model of where the solar wind initially encounters resistance from interstellar matter was displaced by an interval wider than the outer planetary system. The location represented a complication. But what transpired at the threshold was more troubling. Anomalous cosmic rays were expected to peak at the termination shock. This ranked among the most reliable predictions in heliophysics. These particles, neutral atoms that had been ionized and accelerated, were understood to acquire their immense energies through a mechanism termed diffusive shock acceleration, rebounding repeatedly across the shock front, comparable to a projectile gaining momentum between two converging barriers. When Voyager traversed the shock, the anomalous cosmic ray density should have surged dramatically. It did not surge. The density persisted in climbing. It continued ascending as Voyager penetrated deeper into the heliosheath, beyond the shock and toward the heliopause. The termination shock was not the acceleration location, or at minimum not along this trajectory. Decades of theoretical development regarding anomalous cosmic ray acceleration dissolved with a single collection of measurements. Stamatios Krimaigas, the principal investigator overseeing Voyager's low-energy charged particles experiment, had constructed sensors that visited all 8 planets. His detector was the one registering cosmic ray data as Voyager traversed the shock front. The particles his sensor documented were genuine. Their energies were genuine, but they were not behaving as every theoretical framework demanded they should at this threshold. The immediate inquiry became where the acceleration was genuinely occurring. Some researchers hypothesized that anomalous cosmic rays might undergo acceleration at the flanks of the heliosphere, the lateral surfaces of the bubble rather than the forward face. Voyager was traveling roughly toward the forward face. If the flanks represented the true acceleration zone, Voyager would have passed through the shock without detecting the maximum. This would account for the measurements, but introduced a new complication. No spacecraft has ever traveled toward the heliosphere's flanks. No mission is presently scheduled to do so. 22 years afterward, in 2026, the origin of anomalous cosmic ray acceleration remains unidentified. The particles exist. The energies are registered. The acceleration is genuine, and we cannot determine where it originates. Voyager 2 introduced another complication 3 years subsequently. On August 30, 2007, the second probe traversed the termination shock at roughly 83.6 astronomical units. That is 10 astronomical units nearer than Voyager 1's crossing point. 10 astronomical units equates to approximately 1.5 billion kilometers. The heliosphere was not simply smaller than predicted. It was asymmetric, compressed on one aspect, driven inward by influences the theoretical models had failed to incorporate. Two traversals, two contrasting distances. The initial threshold already incorrect in both position and behavior. And Voyager 1 remained more than a decade removed from the heliopause where the genuine discoveries awaited. There exists a detail about Voyager, one that fundamentally alters how the entire investigation develops. In 1980, during the Saturn flyby, the spacecraft's plasma science instrument malfunctioned. The plasma science experiment, designated PLS, served as the principal tool for direct measurement of charged particle populations. It could enumerate ions and electrons, establish their velocities, and determine their temperatures. It was the instrument engineered to characterize the heliopause crossing. It broke 32 years before the crossing it was constructed to detect. When Voyager 1 eventually approached the heliopause in 2012, it arrived absent its most critical sensor. Envision examining a crime scene lacking the capacity to collect fingerprints. You can still observe, still capture images, still take other measurements. But the direct evidence you require most is the single thing you cannot gather. This reduction left Donald Gurnett's plasma wave subsystem as the sole instrument capable of measuring plasma density by indirect means. The device has a mass of 1.4 kilograms, approximately equivalent to a modest hardcover volume. It draws 1.6 watts of electrical power, less consumption than a night lamp, and NASA originally declined to include it. In the early 1970s, when Voyager's instrument package was being assembled, Gurnett proposed a comprehensive plasma wave receiver. NASA's evaluation board refused. The spacecraft was already carrying excessive mass. Gurnett returned with a revised proposal in 1973. He restructured his instrument as a compact, spectral analyzer that could share the antenna structures already designated for the planetary radio astronomy experiment. Share the antennas, reduce the mass, obtain the measurement. NASA consented. The instrument that would ultimately validate humanity's inaugural crossing into interstellar space nearly did not make the journey. The plasma wave subsystem operates differently from the plasma science instrument. PLS measures particles directly. PWS listens for wave activity. Specifically, it registers oscillations in the electrical field generated by electrons vibrating within the ambient plasma. The frequency of these oscillations is determined by the electron density of the surrounding medium. Higher density produces higher frequency. Through measuring the frequency, one can calculate the density. Through calculating the density, one can establish whether the spacecraft is immersed in the tenuous solar wind plasma or the denser interstellar plasma. This distinction mattered because the heliopause was characterized in part by a pronounced elevation in plasma density. On the solar side, the plasma is rarefied, dominated by particles propelled outward from our Sun. On the interstellar side, the plasma is denser, constituted of matter unconnected to our solar system. If Gurnet's instrument could register that density elevation through its frequency measurements, it could confirm the crossing even without the primary sensor. But a complication existed. PWS can only quantify plasma density when something agitates the plasma sufficiently to trigger measurable oscillations. Under quiescent conditions, there is nothing to register. The instrument remains inactive, awaiting disturbance in the surrounding medium. This implied that confirmation might not arrive at the moment of crossing. It might come weeks or months afterward whenever a solar eruption dispatched a pressure front rippling outward to reach Voyager's location and disturb the local plasma into oscillation. The mission's most critical measurement would depend upon a non-functional primary instrument. A declined backup with less mass than a bag of granulated sugar, and the responsiveness of the interstellar medium itself. Everything needed to align, and Voyager 1 was already inside the heliosheath, navigating through a region bearing no resemblance to what anyone had anticipated. The heliosheath was expected to be structured. Theoretical frameworks depicted the solar magnetic field curving smoothly throughout this zone, the field lines bending like the grain in finished timber as the solar wind decelerated and spread laterally after traversing the termination shock. Spacecraft would transit through a layered, organized environment where magnetic field orientation shifted gradually and predictably. Between 2007 and 2008, both Voyagers encountered something entirely different. The heliosheath was populated with magnetic bubbles, not smooth curvatures. Bubbles, each approximately 1 astronomical unit in diameter, roughly 150 million kilometers, the separation between Earth and our Sun. The magnetic field in the outer heliosphere was not flowing in orderly arcs. It was fragmenting through a process called magnetic reconnection, where field lines rupture and reorganize into closed loops. The consequence was a churning froth of magnetic islands extending across the entire outer margin of the solar system. Visualize it thus: you anticipated discovering a neatly stratified arrangement. Instead, you discovered a vessel overflowing with soap foam, each bubble the diameter of Earth's orbital path around our Sun. This turbulent configuration carried consequences for everything else. Cosmic rays, both the galactic variety arriving from beyond and the anomalous type accelerated somewhere within the heliosphere, had to navigate this magnetic obstacle course. The bubbles could confine particles, redirect them, decelerate or accelerate them in ways no smooth field model could anticipate. The failure to detect the anomalous cosmic ray peak at the termination shock suddenly possessed a potential contributing explanation. If the heliosheath constituted a labyrinth of magnetic bubbles, the simplified model of particles bouncing back and forth across a clean shock face was fundamentally inadequate. The bubbles also raised questions regarding how the heliosphere interacts with the interstellar medium at the heliopause. If the solar side of the boundary constitutes a frothy turbulence rather than a smooth barrier, the contact zone between solar and interstellar material might be irregular as well. The clean, sharply defined heliopause of the reference texts was already appearing questionable. Voyager 1 spent nearly 8 years traversing the heliosheath. the separation from the termination shock at 94 astronomical units to the heliopause at 121.6 astronomical units was approximately 27.6 astronomical units, and at Voyager's velocity of roughly 61,000 kilometers per hour, covering that interval required from December 2004 to August 2012. Throughout those years, the magnetic bubble data accumulated. Researchers released publications, models underwent revision, but the definitive examination would arrive at the heliopause itself, where the solar magnetic field encounters the interstellar magnetic field and the plasma density elevates by an order of magnitude. Every theoretical model declared that crossing would be unambiguous. The magnetic field direction should pivot dramatically like a compass needle swinging from north to east. Particle populations should reverse, solar particles vanishing and galactic particles flooding inward. Plasma density should jump decisively. All three signatures combined would delineate the threshold. Voyager 1 reached that threshold on August 25, 2012. The particle measurements cooperated. Solar particle counts declined. Galactic cosmic ray counts surged. But the magnetic field did not pivot. It barely shifted. The eye saw a single, most anticipated signature of the heliopause crossing, the one researchers had awaited 35 years to witness, failed to appear. And because it failed to appear, no consensus could form regarding what had just transpired. On August 25, 2012, Voyager 1 was positioned 121.6 astronomical units from our Sun. That translates to roughly 18 billion kilometers. The spacecraft had been traveling for 35 years. Its radio transmission propagating at the velocity of light required 17 hours to arrive at Earth. The data it relayed showed two distinct transitions. Galactic cosmic ray intensity elevated to levels surpassing any previous measurement across the mission's history. Solar energetic particle counts descended to near zero. By these measures alone, Voyager 1 had departed the heliosphere and entered interstellar territory. But NASA issued no declaration, convened no press event, staged no commemoration. The reason was the magnetometer. The magnetic field magnitude had shifted marginally, at the boundary. The orientation had not. Every theoretical model of the heliopause predicted that the solar magnetic field and the interstellar magnetic field would point in opposing directions. The transition between them should generate a measurable swing in field orientation. Imagine walking from a chamber where all furnishings face northward into a room where everything faces eastward. You would register the change instantly. Voyager's magnetometer registered nothing. The field on both sides of the crossing pointed in essentially identical directions. The difference was so negligible it could barely be isolated from instrumental background noise. Edward Stone, the project scientist who had guided the mission from 1972, could not declare the crossing without the magnetic signature. The particle measurements indicated Voyager had crossed. The magnetic measurements indicated it had not. And, absent the plasma science instrument, which had been non-functional since 1980, no direct plasma measurement existed to resolve the disagreement. This stalemate persisted for over a year. From August 2012 to September 2013, the status of Voyager 1 remained officially unresolved. The most distant human-constructed object had either entered interstellar territory or it had not, and the two sets of onboard instruments held opposing positions. The heliopause had been forecast at 150 astronomical units. Voyager had encountered it at 121.6. The threshold was 20% nearer than anticipated, and now the threshold itself was declining to behave as modeled. Researchers released competing interpretations. Conference sessions transformed into debates. The heliophysics community was divided by a spacecraft that had accomplished precisely what it was supposed to, except the boundary it traversed resembled no model's predictions. The missing magnetic reversal represented the anticipated definitive signature. Models had calculated the interstellar magnetic field orientation based on starlight polarization patterns, the architecture of the local interstellar cloud, and the distribution of nearby stellar magnetic configurations. The solar magnetic field direction was well established from decades of direct measurement. The two should have been offset by a substantial angle. The fact of their alignment presented a question nobody could resolve quickly. Were the theoretical models of the interstellar field inaccurate? Was the threshold producing an unexpected effect on the field? Or had Voyager genuinely not traversed the heliopause at all? For 13 months, the inquiry stalled at this question, and the resolution when it arrived would depend entirely upon the 1.4-kilogram instrument that NASA had nearly declined 4 decades prior. The scientific community did not await resolution with patience. The debate regarding whether Voyager 1 had traversed the heliopause became one of the most publicly visible disagreements in space physics. Len Fisk and George Gloeckler, both established heliophysicists with decades of publications, argued that Voyager 1 had not entered interstellar space. Their interpretation was precise. The spacecraft had entered what they termed a depletion region, a zone where solar energetic particles could escape along magnetic field lines while the magnetic field itself retained solar characteristics. In their framework, the particles departed, but the field remained. Voyager was still within the heliosphere, merely inhabiting an unusual sector of it. The argument possessed internal consistency. It accounted for the particle decrease, it accounted for the unchanged magnetic field, and it preserved the reference text model of the heliopause intact. On the opposing side stood Donald Gurnett. He was not debating, he was waiting. Gurnett's plasma wave subsystem required the interstellar medium to oscillate. Without agitation, the instrument had nothing to register. Throughout the 2012 and into early 2013, the plasma surrounding Voyager 1 remained quiet. The PWS recorded sustained low-intensity readings, no oscillation events of sufficient magnitude to compute electron density. Then, on April 9, 2013, the medium responded. A coronal mass ejection, a burst of solar plasma launched from our Sun months earlier, had finally completed the 18 billion kilometer journey to Voyager's position. Upon arrival, it compressed the ambient plasma and triggered oscillations that the PWS could detect. The instrument registered a plasma frequency between 2 and 3 kilohertz. This measurement carried the answer. In the rarefied solar wind plasma inside the heliosphere, plasma oscillation frequencies fall around 300 hertz. In the denser interstellar medium, the frequency should be substantially higher. The 2 to 3 kilohertz measurement corresponded to an electron density of roughly 0.08 particles per cubic centimeter. This was consistent with the anticipated density of interstellar space. It was an order of magnitude higher than the solar wind density. Gurnett's team published their findings in the journal Science. On September 12, 2013, NASA convened the press conference. Voyager 1 had entered interstellar space on August 25, 2012. Confirmation arrived 13 months after the occurrence, and it came from a 1.4 kilogram instrument drawing 1.6 watts of power. An instrument that existed solely because its designer had consented to a shared antenna compromise 4 decades prior. The Fisk and Glaucler model was not technically disproven. Their interpretation remained consistent with the magnetic measurements, but Gurnet's plasma density reading placed the spacecraft definitively within interstellar plasma, and the density value was too high to represent any configuration of solar wind, compressed or otherwise. The depletion region hypothesis could not reconcile with the electron density. The community advanced, but the more fundamental question persisted unresolved. The magnetic field at the heliopause had not behaved as predicted. The leading explanation proposed that the interstellar magnetic field drapes across the heliosphere like a sheet over a sphere, orienting itself along the contact surface. This draping mechanism could bring the two fields into approximate alignment at the crossing point. It represented a physically plausible mechanism, but no theoretical model had anticipated it before the crossing. It was developed retrospectively to account for the measurements after the fact. The heliopause was supposed to yield a clean magnetic signature. It produced the reverse, and the inquiry into what the boundary actually resembles was only beginning. Edward Stone was 26 years of age when he joined the Voyager project in 1972 as its project scientist. He would maintain that position for 50 years, retiring in 2022 at age 76. Across that half-century, he coordinated 11 science teams through encounters with Jupiter, Saturn, Uranus, and Neptune. He directed the Jet Propulsion Laboratory from 1991 to 2001, overseeing 24 missions including Mars Pathfinder and the Mars Exploration Rovers. He also served as principal investigator for the Cosmic Ray Subsystem, the instrument that registered the anomalous cosmic ray measurements at the termination shock. Stone was the person journalists contacted when Voyager data arrived. He was the voice that converted plasma density measurements and magnetic field vectors into language accessible to the public. When Voyager 2 passed Neptune in 1989, Stone was present at the Jet Propulsion Laboratory. When Voyager 1's particle measurements shifted at the heliopause in 2012, Stone was the individual who declined to announce the crossing until the evidence was conclusive. That caution, that insistence on awaiting Gurnet's plasma wave data before making any declaration, cost NASA a year of coverage, but preserved the mission's scientific integrity. In June of 2024, Edward Stone passed away. He had witnessed his spacecraft reach interstellar territory. He had observed the confirmation press event in 2013. He had reviewed the data from Voyager 2's crossing in 2018. The mission he dedicated his professional existence to building had now outlasted him. Suzanne Dodd assumed the Voyager project manager role in 2010, 2 years before the heliopause crossing. She guided the team through both boundary traversals, the 2023 communications breakdown when Voyager 1 began transmitting incoherent data, and the continuing instrument decommissionings that are incrementally eliminating both spacecraft's sensing capabilities. Dodd once characterized the Voyagers as deep space legends. She now makes the most consequential decisions in the mission's history. Which sensors to deactivate, which measurements to forfeit, which observational windows to permanently close as the power budget erodes. The scope of Stone's tenure resists description without comparison. Consider that Stone joined Voyager the same year as the Watergate break-in. He was still directing the project when the original iPhone launched. The mission bridged the personal computing transformation, the Internet era, the smartphone age, and the emergence of commercial spaceflight. Year after year, Stone arrived and managed the data. His cosmic ray instrument delivered one of the mission's most consequential findings at the termination shock. The failure of anomalous cosmic rays to peak as predicted was not incidental. It invalidated the acceleration mechanism that Stone's own research community had constructed over decades. The principal investigator's instrument refuted the principal investigator's entire scientific domain. Stone reported the result without editorial comment. Tom Kremigis, whose low-energy charged particles experiment traversed all 8 planets, witnesses his instruments deactivated one by one. John Richardson, at the Massachusetts Institute of Technology, constructed the plasma science instrument aboard Voyager 2 that would subsequently provide the only direct plasma measurements at the heliopause, data that Voyager 1 could never gather due to the 1980 instrument failure. The human continuity of Voyager carries significance because spacecraft do not interpret data. Humans do. The debates, the disagreements between Fisk and Gurnett, the decisions regarding which sensors to keep active, all of these represent human determinations rendered under conditions of incomplete knowledge. Stone made those determinations for 50 years. Dodd makes them presently, and the data arriving after the heliopause crossing revealed an interstellar medium that no one had modeled accurately. The temperature of the local interstellar medium was forecast to fall between 15,000 and 30,000 degrees Kelvin. This interval derived from models of the local interstellar cloud, the region of diffuse gas our solar system is presently traversing. The models incorporated heating contributions from neighboring stars, radiative cooling, and the general thermodynamic properties of low-density hydrogen and helium gas. 30,000 Kelvin was treated as the upper ceiling. Most estimates concentrated near 20,000. Voyager's sensors registered temperatures between 30,000 and 50,000 Kelvin. At the lower end, the measurement corresponded only to the extreme edge of predictions. At the upper end, it exceeded them by 67%. The interstellar medium immediately exterior to our heliosphere was considerably hotter than the prevailing model permitted. The measurement seems counterintuitive because the term temperature can mislead at these densities. Temperature in physics characterizes the average velocity of particles. In the interstellar medium, the particles travel rapidly. This produces a high temperature reading, yet there are almost no particles present. The density approximates 1 atom per 10 cubic centimeters of space. Contrast that to ordinary indoor air, which contains roughly 800 billion molecules per cubic centimeter. The interstellar medium is so evacuated that even at 50,000 Kelvin, you would perish from cold within seconds. The particles are rapid, but they are too scarce to transfer meaningful thermal energy to any object. This distinction between temperature and heat content matters because it governs how the heliosphere interacts with its environment. A hotter interstellar medium applies greater thermal pressure to the heliosphere's boundary. Elevated pressure causes the heliosphere to contract. This constitutes one reason both the termination shock and heliopause were positioned nearer than predicted. The exterior was applying greater force than anyone had calculated. The origin of the surplus heat points beyond our solar system entirely. Our sun occupies a structure termed the local bubble. a cavity roughly 1,000 light-years across that was excavated by supernova detonations over the preceding 10 to 20 million years. These explosions dispatched shock fronts through the interstellar medium, compressing gas, elevating its temperature, and leaving behind a hot, low-density environment. The elevated temperatures Voyager measured are not a localized anomaly. They are the enduring signature of stellar explosions occurring millions of years prior to our solar system's formation in its present configuration. This connection between ancient stellar explosions and present-day measurements at the heliosphere's boundary ranks among the most underappreciated aspects of the Voyager discoveries. The frontier of our solar system is shaped by our sun propelling particles outward. It is simultaneously shaped by long-dead stars exerting pressure inward. The heliosphere exists at the convergence of these opposing forces, and the equilibrium between them determines where the boundaries reside, how extensive they are, and whether the bubble we inhabit is expanding or contracting at any particular moment. The 11-year solar cycle causes our sun's output to oscillate, extending the heliopause outward during solar maximum and permitting contraction during solar minimum. Researchers estimate the threshold migrates by 10 or more astronomical units across a complete cycle. The heliosphere inhales and exhales, and the temperature of the ambient medium determines the intensity of external resistance during each contraction. Voyager registered the external temperature, but it also began measuring density once it crossed the heliopause, and those density measurements would expose something that remains without explanation: a gradient that has been ascending for years and shows no indication of plateauing. When Voyager 1 traversed the heliopause on August 25, 2012, it began registering the density of interstellar plasma via its plasma wave subsystem. The initial readings placed the electron density at roughly 0.055 particles per cubic centimeter. This fell within the anticipated range. Theoretical frameworks of the local interstellar medium forecast densities somewhere between 0.04 and 0.07 particles per cubic centimeter at the heliopause. For once, a Voyager measurement arrived where theory indicated it should. Then the density began rising. Across the subsequent years, the electron density elevated to 0.12, then to 0.15 particles per cubic centimeter. That represents nearly 3 times the initial measurement. Voyager was traveling in a direct path through interstellar space at roughly 61,000 kilometers per hour, and the medium it was traversing kept becoming denser. No theoretical model predicted this gradient. The interstellar medium was expected to be roughly homogeneous at these scales, with density variations only across distances of light years, not the tens of astronomical units Voyager was covering. Beginning around 2020, the density elevation intensified. Researchers identified what they termed Pressure Front 2, a zone where plasma density surged roughly 30% above the already elevated baseline and remained there. As of early 2026, Voyager 1 has been within this elevated density zone for more than 5 years. The front displays no indication of terminating. To grasp why this confounds understanding, consider the distances involved. 1 astronomical unit spans roughly 150 million kilometers. Voyager 1 has covered roughly 43 astronomical units since traversing the heliopause. Across that interval, the density has nearly tripled. This resembles walking across a playing field and discovering that air pressure at the far end stands 3 times higher than at the near end, with no intervening wall or barrier. Something is compressing the interstellar medium in the zone Voyager is entering, and the source of that compression is unidentified. Several hypotheses have been advanced. One proposes that Voyager is approaching a denser sector of the local interstellar cloud, a natural variation in the irregular structure of gas between star systems. Another suggests that a compression front from a remote origin, perhaps connected to the same supernova remnants that formed the local bubble, is propagating through the medium. A third possibility is that the heliosphere itself is accumulating interstellar material at its leading edge, the way a vessel generates a bow wave in water. None of these explanations fully reconciles with the duration and scale of the increase. Pressure front 2 has persisted longer than any transient phenomenon should across these scales. The data continues arriving every 45 hours, and the gradient continues defying theoretical frameworks. The density measurements connect directly to the persistent vibration Voyager began detecting in 2017. The vibration represents a narrowband plasma emission, whose frequency correlates with local electron density. As the density elevates, the characteristics of the vibration shift. Together, they disclose that the interstellar medium possesses structure at scales of tens of astronomical units and pressure gradients that endure for years without explanation. Voyager 1 spent 6 years as the sole human-constructed object in interstellar space. Then, in 2018, it gained a counterpart, and what the second probe measured at the boundary failed to match what Voyager 1 had detected. The instrument Voyager 2 carried into interstellar space was designated the Plasma Science Experiment, or PLS. It was developed at the Massachusetts Institute of Technology under John Richardson's direction. Its mandate was straightforward: orient toward incoming particles, register their velocity, temperature, and density. Voyager 1 had carried the identical instrument once. It malfunctioned during the Saturn flyby in 1980, 32 years before the heliopause crossing it was designed to register. Voyager 2 would not encounter that complication. On November 5, 2018, Voyager 2 traversed the heliopause at roughly 119 astronomical units from our Sun. Richardson's instrument recorded something unambiguous. The plasma density surrounding the spacecraft elevated from roughly 0.002 particles per cubic centimeter to 0.039. That constitutes a 20-fold increase. To frame that in physical terms, envision walking through a space where a single grain of sand floats within a volume equivalent to a large shipping container. Then stepping through a doorway and encountering 20 grains in the identical volume. Still, essentially nothing by terrestrial standards. But in the diffuse medium between star systems, that jump is the equivalent of encountering a wall. The elevation confirmed that Voyager 2 had crossed the heliopause. It was now the second human-constructed object in interstellar space. But the particulars of the crossing failed to correspond to what Voyager 1 had experienced 6 years earlier. Voyager 1 had crossed at 121.6 astronomical units. The separation amounts to about 2.5 astronomical units, or roughly 375 million kilometers. The two spacecraft were traveling in diverging directions. Voyager 1 proceeded roughly toward the nose of the heliosphere, the direction our solar system plows through the interstellar medium. Voyager 2 traveled at a contrasting angle, southward of the ecliptic plane. Theoretical models predicted that both traversals would appear fundamentally similar, because the heliopause was expected to be a uniform boundary. It was not. Voyager 1 occupied a peculiar transition zone for months where energetic particles dropped, but the magnetic field declined to change direction. Voyager 2 encountered something cleaner. The boundary was thinner. The plasma transition was sharper. The magnetic field shifted more perceptibly, though still not as dramatically as decades of theoretical models had required. The heliosheath, the turbulent region between the termination shock and the heliopause, was also contrasting for each probe. Voyager 1 traversed roughly 27.6 astronomical units of heliosheath. Voyager 2 crossed approximately 35.4 astronomical units of it. That is nearly 8 astronomical units of difference, approximately 1.2 billion kilometers. Same region, same boundary, two fundamentally dissimilar experiences. Scientists had anticipated Voyager 2 would corroborate what Voyager 1 had discovered. Instead, it contradicted it. The heliopause was not a uniform shell wrapped consistently around our sun. It was irregular, thicker in certain locations, thinner in others, configured by external forces pressing inward. Two data points from two contrasting directions generated two contrasting pictures, and, absent a third spacecraft directed toward the boundary, no tie-breaking measurement was available. The inquiry possessed two witnesses. They disagreed, and the disagreement indicated something larger than either crossing alone could illuminate. The heliosphere itself was not the shape anyone had depicted. The asymmetry had manifested before Voyager 2 reached interstellar territory. It emerged the moment Voyager 2 encountered the termination shock. On August 30, 2007, Voyager 2 traversed the termination shock at roughly 83.6 astronomical units. Voyager 1 had traversed the identical boundary on December 16, 2004 at 94.01 astronomical units. The separation exceeded 10 astronomical units, approximately 1.5 billion kilometers. That is roughly 10 times the Earth-to-Sun separation. The heliosphere was being compressed asymmetrically. On one aspect, the termination shock was positioned nearer. On the other, it extended farther out. Something external was exerting greater pressure on the southern flank. The interstellar magnetic field was the principal suspect. Measurements from both voyages indicated that the magnetic field threading through the space between star systems was non-uniform. It pressed against the heliosphere at an oblique angle, compressing one aspect more than the other. The bubble our solar system generates in space was uneven, comparable to a balloon being pressed against a surface from a single direction. In 2008, a year following Voyager 2's termination shock crossing, NASA launched a compact spacecraft called the Interstellar Boundary Explorer, designated IBEX. It did not travel to the heliosphere's margin. Instead, it orbited Earth and oriented its detectors outward, capturing energetic neutral atoms, or ENAs, traveling inward from the boundary zone. These atoms form when charged particles from the solar wind exchange electrons with neutral interstellar atoms. They travel in straight lines unaffected by magnetic fields, carrying information about boundary conditions back toward Earth like dispatched couriers. IBEX discovered something nobody had predicted. Across the celestial sphere there existed a narrow ribbon of concentrated energetic neutral atom emissions. It constituted a band, roughly circular, stretching across the sky. No theoretical model had generated anything resembling it. The ribbon's location corresponded to where the interstellar magnetic field was perpendicular to the line of sight from Earth. That correlation was unambiguous. The explanation was not. The ibex ribbon implied the heliosphere's interaction with the interstellar medium was far more structured than any model had depicted. The boundary was not a gradual compression zone, transitioning smoothly from solar to interstellar material. It had distinguishing features. It had concentrated zones of particle interaction that depended upon the external magnetic field geometry. The interstellar medium was actively sculpting our bubble from outside. Combined with the 10 astronomical unit asymmetry and termination shock location, the picture was crystallizing. The heliosphere was not a uniform sphere, and it was not static. It was dynamic, asymmetric, and responsive to external influences that theoretical models had either underestimated or entirely disregarded. The shape of our solar system's protective enclosure depended as much on what existed outside it as on what our sun propelled outward from within. The ibex ribbon persists unexplained to this day. Multiple theoretical frameworks exist. One proposes the ribbon forms where neutral interstellar atoms are ionized by the solar wind, captured by the interstellar magnetic field, and subsequently reneutralized, dispatching energetic neutral atoms back toward Earth from a specific geometric configuration. Another proposes that the ribbon traces a zone where the interstellar magnetic field drapes across the heliosphere and generates a secondary particle population. Neither framework fully reproduces what ibex detected. The ribbon was a discovery that generated more questions than it answered, and it directed attention toward a more fundamental problem. If the heliosphere lacked a spherical form, what about the feature upon which every scientific reference had agreed? What about the tail? For more than 50 years, every diagram of the heliosphere incorporated a tail. It resembled a comet. Our sun moved through the interstellar medium, and the solar wind streaming behind it was expected to extend into a prolonged wake trailing hundreds of astronomical units downwind. The geometry was intuitive. It matched the behavior observed when air streams into a moving current. The forward face compresses, the trailing edge extends. Scientific texts reproduced it, educational posters displayed it, visualizations rendered it. The comet tail heliosphere was among the most recognizable images in space science. In 2017, data from the Cassini spacecraft eliminated it. Cassini spent 13 years orbiting Saturn, but one of its instruments, the ion and neutral camera, was oriented outward, capturing energetic neutral atoms from the heliosphere's boundary, the identical particle type that ibex was designed to detect. Cassini possessed an advantage. It observed across a complete 11-year solar cycle. This meant it could monitor how the boundary responded to variations in solar output over time. When our sun's activity elevated, particles at the boundary should respond. The question concerned how rapidly that response traveled to contrasting sectors of the heliosphere. If an extended tail existed, particles from the tail direction would require substantially longer to respond to solar variations. The signal would need to traverse hundreds of astronomical units down the tail and subsequently return as energetic neutral atoms. There would be a measurable delay relative to particles arriving from the nose direction where the boundary was nearer. There was no delay. Particles from the tail direction responded to solar variations precisely as rapidly as particles from the nose direction. The response was symmetric. Equal transit time from every direction indicated equal separation in every direction. No extended tail. The heliosphere was roughly equivalent in scale in all directions. Envision anticipating a current extending behind a vessel, and instead discovering that the vessel rests in the center of a still lake. The wake simply did not exist. Mayor of Ophir and colleagues at Boston University proposed an alternative. Their magneto-hydrodynamic simulations suggested the heliosphere might be configured like a croissant, with two jets of matter extending from the poles of our sun's magnetic field and curling back on themselves. Not a sphere, not a comet, something more unusual. The model accounts for some of the data, but not all of it. Other researchers proposed a more compact, roughly spherical geometry. The debate persists unresolved. What is not debated is the absence of the tail. 5 decades of reference text illustrations were incorrect. The most fundamental geometric characteristic of the heliosphere, the single feature upon which universal agreement existed, did not exist. Every space agency digital resource, every introductory astronomy course, every documentary examining the heliosphere had displayed the identical elongated form with a streaming tail. All of them depicted something that Cassini demonstrated does not exist. The Cassini data was published just months before the spacecraft's deliberate atmospheric entry at Saturn in September 2017. Among its final scientific contributions was the demolition of one of the oldest assumptions in heliophysics, and the absence of the tail carried implications beyond geometry. It transformed the pressure equilibrium. Without a prolonged trailing wake dissipating solar wind energy downstream, greater pressure required accounting at the boundary itself. The energy that models had assumed was bleeding away into a tail was actually remaining concentrated near the heliosphere. The calculations were about to fail to reconcile. When physicists examine a boundary separating two distinct media, among the initial things they verify is pressure equilibrium. The pressure directed outward from within must roughly balance the pressure directed inward from without, or the boundary migrates. At the heliopause, outward pressure originates from the solar wind, its embedded magnetic field, and energetic particles such as cosmic rays. Inward pressure originates from the interstellar plasma, its magnetic field, and whatever additional constituents exist in the local interstellar medium. Scientists summed every known pressure contribution from both sides. The values failed to reconcile. The aggregate measured pressure at the heliosphere's margin exceeded any model's prediction. More pressure was directed inward than the known components of the interstellar medium could account for. Something was absent from the equation. An unidentified pressure contribution was acting on the boundary, and nobody could identify its origin. This was not a negligible discrepancy. IBEX's data demonstrated that the aggregate pressure at the heliopause exceeded model predictions by roughly 25 to 50% when employing all known contributing factors. That is equivalent to an entirely unaccounted pressure contribution the magnitude of the thermal plasma contribution. Envision constructing a dam, computing the water pressure on one face and the structural capacity on the other, and discovering the dam remains intact, even though your equations indicate it should have failed. Something you have not measured is providing reinforcement to the structure. Several theoretical frameworks exist. Some researchers propose the interstellar magnetic field is more intense than present measurements indicate, supplying additional magnetic pressure. Others identify populations of energetic particles in the interstellar medium that current instruments cannot register. A third possibility involves the architecture of the interstellar medium itself. Voyager 1's density measurements revealed plasma density ascending steadily following the heliopause crossing from 0.055 particles per cubic centimeter to values between 0.12 and 0.15. Beginning around 2020, Voyager 1 entered a zone researchers designate Pressure Front 2, where density surged an additional 30% and remained there for more than 5 years. No theoretical model predicted this zone. No explanation has achieved consensus. The pressure imbalance connects to every other anomaly. The absent tail means more energy concentrates near the boundary. The asymmetric configuration means pressure distribution is non-uniform. The porous heliopause that the subsequent crossing would reveal means material migrates across the boundary, further complicating the accounting. This is not a circumstance where one measurement was marginally inaccurate. The entire framework for comprehending the heliosphere's pressure environment was incomplete. Every boundary condition scientists employed to model the heliosphere depended on assumptions regarding external pressure that proved incorrect. The termination shock was incorrectly positioned because external pressure exceeded predictions. The heliopause was nearer than anticipated for identical reasons. The geometry was incorrect because pressure distribution was non-uniform. And now the aggregate pressure budget contained a gap that no identified component could bridge. Something in the interstellar medium surrounding our solar system was exerting force that we could quantify through its effects, but could not identify at its source. The boundary was holding. The mathematics indicated it should not be. And Voyager 2's plasma instrument was about to reveal another reason the established framework could not persist. The textbook characterization of the heliopause was unambiguous. On one side, solar wind. On the other side, interstellar plasma. A sharp demarcation. Cross it, and you depart our sun's domain entirely. That was the prediction. Voyager 2's plasma science instrument discovered something different. As the spacecraft approached and subsequently crossed the heliopause in November 2018, Richardson's instrument detected solar wind particles beyond the threshold. Material originating from our sun was permeating interstellar space. The barrier had gaps. This was not entirely unexpected in retrospect. Voyager 1 had suggested something comparable 6 years earlier, though it lacked the appropriate instrument to measure it directly. In the months preceding Voyager 1's confirmed crossing, the spacecraft entered a peculiar transition zone that scientists designated the magnetic highway. In this zone, energetic solar particles dropped sharply while galactic cosmic rays surged, but the magnetic field did not shift direction. The field lines retained solar characteristics, remaining connected back to our sun, even as the particles traversing those field lines were interstellar in origin. Envision a highway running along an international border. The road infrastructure belongs to one nation, but the vehicles on it originate from the opposite side. The infrastructure is solar. The traffic is interstellar. Particles from beyond were streaming inward along magnetic field lines originating from our sun. While solar particles escaped outward along the same pathways, the boundary was not a barrier. It resembled something closer to a membrane, selectively permeable in both directions. Voyager 2's direct plasma measurements confirmed and elaborated this picture. The transition at the heliopause was not instantaneous. A mixing zone existed where solar and interstellar plasmas coexisted. The boundary possessed thickness. It possessed architecture. Solar material did not simply terminate at the margin. It permeated through, carried along magnetic field lines draped across the heliopause like fabric over a framework. The technical designation for this is helioporosity. The boundary permits material passage in ways contingent upon local magnetic field geometry. Where field lines connect across the boundary, particles flow. Where they do not, the boundary holds. The result is a patchy, inconsistent frontier that varies across locations and likely across years as the magnetic field configuration evolves with the solar cycle. This porosity carries consequences. If solar material leaks outward, it transports energy and momentum with it, affecting the pressure equilibrium at the boundary. If interstellar material permeates inward, it alters the composition of the outer heliosphere. The clean two-fluid model, solar wind interior and interstellar plasma exterior, was overly simplified. Reality constituted a mixed zone where the two media interpenetrated. The porosity also raised a concern regarding protection. The heliosphere shields the inner solar system from a significant fraction of galactic cosmic radiation. If the boundary leaks, that shielding is not absolute. The extent of leakage, how it varies with location and solar cycle, and whether it affects the radiation environment deeper within the heliosphere, all remain open questions. Voyager 2 sampled only a single point on a boundary that encircles the entire solar system. With the boundary revealed as porous, the heliosphere's form unresolved, and the pressure equations imbalanced, the inquiry required something the Voyagers could not supply. It required a comprehensive view, a way to observe the entire heliosphere simultaneously, rather than sampling it along two narrow trajectories. But before that new capability could become available, the inquiry had one additional discovery awaiting in the data. Voyager 1 had been quietly accumulating measurements since 2017. The interstellar medium was not silent. It was resonating. In the opening section, there was a signal, a persistent narrowband plasma emission detected by Voyager 1's plasma wave subsystem beginning in 2017. At that point, it represented an unexplained signal from interstellar territory. Now, with the complete context of what Voyager has discovered, that signal becomes something more meaningful. The emission occupies a frequency corresponding to the local electron density in the interstellar medium, roughly 0.11 particles per cubic centimeter. The bandwidth is narrow, approximately 0.04 kilohertz wide. It is continuous. It does not commence and cease with solar events. It bears no correlation to anything our sun produces. It is a characteristic of the interstellar medium itself, a background resonance in the space between star systems that nobody anticipated would exist. Before Voyager traversed the heliopause, scientific consensus was straightforward. The interstellar medium near our solar system was frigid, rarefied, and undisturbed. Theoretical frameworks place the temperature at 15,000 to 30,000 Kelvin. The density was minimal. The magnetic field was weak. No basis existed to anticipate activity, architecture, or signal. The region was expected to be the cosmic equivalent of an empty chamber. Voyager discovered a concert venue. Plasma temperature measured between 30,000 and 50,000 Kelvin, up to 67% more energetic than the upper ceiling of predictions. The density exceeded expectations and continued climbing. And the resonance was present, persistent, and steady, the acoustic indicator of a medium that was anything but undisturbed. Analysis of the resonance by Stella Koch-Ocker and colleagues exposed something deeper. The density fluctuations encoded within the signal adhered to a pattern termed the Kolmogorov turbulence spectrum. This represents a specific mathematical relationship between the dimensions of turbulent eddies and their energy content. Initially characterized by the Russian mathematician Andrei Kolmogorov in 1941. When a fluid exhibits turbulence, energy cascades from large dimensions down to small dimensions in a predictable manner. The interstellar medium near our solar system follows this cascade. It exhibits turbulence at scales of astronomical units, the identical unit of distance measuring the Earth-to-Sun separation. Consider it like pressing a medical listening instrument against a building wall and detecting the internal plumbing. You cannot observe the pipes. You are unaware of their arrangement, but the sound communicates that a system exists, that flow occurs, that architecture is present. The interstellar resonance is Voyager's listening instrument pressed against the medium between star systems. And what it detects is not emptiness. It is a fluid in motion, agitated by forces operating at scales vastly exceeding our heliosphere. Those forces almost certainly trace back to ancient stellar explosions. Our solar system occupies the local interstellar cloud, which itself inhabits a larger architecture termed the local bubble, a cavity roughly 1,000 light-years across, carved out by stellar explosions across the preceding 10 to 20 million years. The elevated temperature, the density fluctuations, the turbulence encoded within the resonance are all residual signatures of extinct stars. Energy deposited millions of years ago, still propagating through the medium surrounding our solar system. The silent void scientists anticipated never existed as silence. It was never a void. And the instrument that detected this, Don Gurnet's 1.6-watt plasma wave subsystem, had been operational since 1977, requiring 40 years of waiting for something warranting detection. In late 2023, that instrument nearly ceased permanently. Not through malfunction, but because the spacecraft carrying it commenced transmitting incoherent data. On a day in November 2023, the data stream from Voyager 1 transformed. Where structured scientific telemetry had existed, there was now noise, repetitive patterns of ones and zeros encoding nothing. The most distant human-constructed object, 24 billion kilometers from Earth, was transmitting but no longer conveying meaningful information. The source of the problem resided in the Flight Data Subsystem, or FDS. This constitutes the spacecraft's central processing unit. It collects data from all active instruments, packages it into telemetry frames, and transmits it to the radio for relay to Earth. Every piece of scientific information Voyager 1 had relayed since 1977 passed through this system. The FDS operates on memory components fabricated in the mid-1970s. Its aggregate memory capacity is 69.63 kilobytes. For comparison, a single photograph on a contemporary smartphone occupies roughly 3 to 5 megabytes. The FDS possesses less memory capacity than the text content of a compact novel. One of those memory components had failed. Engineers at the Jet Propulsion Laboratory determined that approximately 3% of the FDS memory was corrupted. That may appear negligible, but 3% of 69.63 kilobytes is not substantial. And the code occupying that region was essential for constructing telemetry frames. Without it, the FDS could not assemble coherent data transmissions. Scientific data stopped flowing. Engineering telemetry stopped flowing. For 5 months, Voyager 1 transmitted meaningless signals across 24 billion kilometers of space. The challenge confronting the engineering team was unlike any repair attempt in the history of space exploration. The spacecraft was more remote from Earth than any human-constructed object ever built. A radio signal traveling at light speed requires approximately 22.5 hours to reach it. This means every instruction dispatched from Earth requires a 45-hour round trip before engineers can observe the outcome. No real-time interaction exists, no control inputs, no visual feed. Every action constitutes a message transmitted across the solar system with a day-long wait for the reply. The code requiring repair was 46 years old. It was composed for hardware that no longer exists anywhere on Earth. The documentation, where it survived at all, described systems conceived by engineers who had long since departed or died. Suzanne Dodd's team at the Jet Propulsion Laboratory had to examine archival code documentation, comprehend the original logic, and determine how to circumvent a physical hardware failure in a processor smaller than a contemporary calculator from a distance that light itself needs nearly a full day to traverse. Envision attempting to repair a mechanical typewriter. The typewriter occupies a secured room. You cannot enter the room. You can only pass written notes beneath the door and wait 22 hours for a response. The typewriter was manufactured in 1977. You possess the original documentation, but several pages are missing, and 3% of the typewriter's keys are stuck in positions producing incorrect characters. That approximates what the Voyager engineering team confronted. Except the room was 24 billion kilometers distant, and the typewriter was the sole example in existence. The team required a method to identify what was broken before they could address it. In early 2024, they formulated a plan. They would transmit a single diagnostic instruction to Voyager 1, an interrogation command. The engineers designated it a poke. On March 3, 2024, the instruction departed Earth. It traveled at the velocity of light across the inner solar system, past the orbital paths of Mars, Jupiter, Saturn, Uranus, and Neptune, through the Kuiper Belt, across the termination shock, through the heliosheath, past the heliopause, and into interstellar territory. 22.5 hours subsequently, it arrived at Voyager 1. The POCA command instructed the Flight Data Subsystem to transmit its complete memory contents to Earth. Not processed data, not packaged telemetry, simply the unprocessed contents of every memory location, corrupted or intact. The spacecraft responded. 22.5 hours after that, the memory dump arrived at the Deep Space Network receiving facilities in California. Engineers now possessed a complete map of the damage. They could identify precisely which memory locations contained corrupted data and which remained functional. The corrupted component held approximately 3% of total memory, and the code stored there was critical for constructing telemetry frames. Data from every instrument passed through routines stored on that component. With those routines corrupted, nothing could exit the system coherently. The resolution was not to repair the component. Repairing a semiconductor from 24 billion kilometers away is not possible. Instead, the team chose to redistribute the affected code to alternative memory locations where functional components had available space. This is roughly equivalent to discovering that one shelf unit in a library has collapsed and, rather than rebuilding the shelf, redistributing the volumes across every remaining shelf with available capacity. The complication was that the code needed to function from its new addresses. Memory locations were hard-coded into the software. Subroutines referenced specific addresses. Relocating the code required rewriting the address references so the system could locate what it needed in unfamiliar locations. Between April 18th and 20th, 2024, the team transmitted the relocated code. Each transmission was a carefully constructed sequence of instructions sent across the solar system and verified after the 45-hour round trip. No margin existed for error. A faulty instruction could crash the FDS entirely, potentially terminating the mission. The team dispatched the corrections in small increments, verifying each one before transmitting the next. On April 20th, engineering telemetry resumed. The data was coherent. The FDS was constructing orderly frames again, routing around the non-functional component the way a roadway routes around a damaged overpass. Engineers spent the subsequent weeks verifying each instrument's data transmission. On May 19, 2024, complete scientific data transmission resumed. Voyager 1 had returned to operation. The repair required roughly 5 months from the onset of incoherent transmissions to the restoration of scientific data. It was performed on a processor with less memory than a contemporary greeting card, operating on code composed during the Carter administration, from a separation so vast that engineers could not engage in dialogue with their own spacecraft. Each exchange was a monologue followed by a day of silence. Suzanne Dodd subsequently characterized the Voyager probes as deep space legends. The characterization is accurate, but it understates the precariousness. The FDS crisis exposed what everyone already recognized but preferred not to address. Voyager 1 is aged. Its components are deteriorating. The corrupted memory component will not represent the final failure. And annually, the power situation worsens. The repair preserved the mission, but it also served as a reminder that the timeline was advancing and was not decelerating. Both Voyager spacecraft are powered by radioisotope thermoelectric generators, or RTGs. These devices extract the thermal energy from decaying plutonium-238 and convert it to electrical current. No moving components exist, no chemical reactions, only the steady inevitable disintegration of radioactive material, generating warmth which thermocouples convert into electrical current. When the Voyagers launched in 1977, each spacecraft's RTGs produced approximately 470 watts of electrical power. That was sufficient to operate all 11 scientific instruments, the communication system, the onboard computers, and the thermal systems maintaining the spacecraft's propellant lines above freezing. Plutonium-238 has a half-life of 87.7 years. This means every 87.7 years, half the remaining plutonium has undergone decay. Power output declines accordingly, diminishing at roughly 4 watts annually. By early 2026, each spacecraft generates approximately 220 watts. That appears adequate until you recognize it must power everything. And everything encompasses thermal systems for propellant lines that would solidify without them. A transmitter broadcasting across 24 billion kilometers. Processors managing attitude control and data handling, and whatever scientific instruments remain active. The arithmetic is merciless. 4 watts of annual loss means roughly 1 instrument's power allocation disappears every few years. Suzanne Dodd and her team at the Jet Propulsion Laboratory confront a decision that no other mission team has faced in quite this manner. They must determine which instruments to deactivate. The deactivations have already commenced. In September 2024, Voyager 2's plasma science instrument was powered down. This was the identical instrument that provided the only direct plasma measurements at the heliopause. John Richardson's device from MIT, the one that registered the 20-fold density elevation in November 2018. That capability is now permanently gone. No other spacecraft carries a plasma instrument directed toward interstellar territory. Those measurements will not be repeated. In February 2025, Voyager 1's cosmic ray subsystem was deactivated. This was Edward Stone's instrument, the one for which he served as principal investigator throughout the complete mission. It detected the anomalous cosmic ray discovery at the termination shock in 2004. It measured the galactic cosmic ray surge that signaled the heliopause crossing in 2012. It is now silent. In March 2025, Voyager 2's low-energy charged particles instrument was deactivated as well. Tom Kremigas constructed that instrument. He is the only scientist in history to have built instruments that traveled to all 8 planets in our solar system. His experiment on Voyager 2 is now dark. By the conclusion of 2026, each Voyager will likely retain only 2 or 3 active instruments. The magnetometer and the plasma wave subsystem are the most power-efficient instruments on both spacecraft. They consume the least current and return the most scientifically significant measurements. They will be the final instruments to cease operation. Engineers estimate they may remain operational into the early 2030s. After that, insufficient power will remain to operate any instrumentation. The transmitters will fall silent. Data flow will cease, and 2 spacecraft will continue drifting through interstellar territory, intact but mute, carrying golden disks that no one will encounter for millions of years. But before that silence arrives, Voyager 1 had one additional surprise concealed within its aging hardware. In October 2024, Voyager 1 ceased responding via its primary X-band transmitter. Instructions from Earth received no reply. The Deep Space Network receiving facilities listened and detected nothing on the anticipated frequency. For a mission that had just endured a 5-month processor crisis, this appeared as though it might represent the conclusion. Then engineers located the signal. It was broadcasting on S-band. S-band is a lower-frequency communications channel that Voyager 1 had not employed since 1981. 43 years earlier, during the Saturn encounter, the spacecraft had transitioned to X-band as its primary communications pathway, because X-band provides superior data rates and enhanced performance across extreme distances. The S-band transmitter was left powered but inactive, a contingency reserve that nobody anticipated would ever be required again. Something prompted Voyager 1 to revert. The precise cause remains under investigation, but the probable explanation involves the spacecraft's fault detection and correction software. When Voyager registered an anomaly with the X-band system, its onboard processing automatically transitioned to the backup configuration. The identical logic that was composed in the 1970s, the identical code that engineers had just completed patching around corrupted memory components, autonomously reached a determination from 24 billion kilometers away. It selected survival. The S-band signal was attenuated. S-band broadcasts at lower power and lower frequency than X-band, meaning the signal disperses more and arrives at Earth with reduced intensity. The Deep Space Network needed to employ its largest receiving structures, the 70-meter antenna dishes, and integrate the signal across. extended intervals to extract coherent data from the background noise. But the data existed. Voyager 1 was communicating. It had simply transitioned to a transmission mode nobody had monitored in 4 decades. Consider the engineering implications. A radio transmitter constructed in the mid-1970s, installed on a spacecraft that launched in 1977, left dormant for 43 years. While the spacecraft traveled from Saturn to interstellar territory, exposed to the radiation environment of the outer solar system and beyond, it activated and transmitted a coherent signal across 24 billion kilometers. The engineering margins incorporated into Voyager's hardware in the 1970s continue yielding benefits half a century afterward. Engineers re-established complete communications and dispatched instructions to transition Voyager 1 back to X-band operation. By November 2024, the spacecraft had returned to its primary transmission configuration. The S-band system returned to dormancy, having executed precisely the function it was designed for 4 decades belatedly. The dormant transmitter episode is minor relative to the FDS crisis or the heliopause crossing. No new scientific discoveries emerged from it. No theoretical models were overturned, but it captures something about the Voyager mission that the science alone fails to convey. These spacecraft were constructed with engineering margins their designers could not have imagined would prove relevant. Nobody in 1977 planned for a 43-year transmitter dormancy test. Nobody engineered the fault protection software anticipating it would reach autonomous determinations from interstellar territory. The engineering was built to be resilient, and that resilience has outlasted every prediction regarding the mission's operational lifespan, the heliosphere's boundaries, and the interstellar medium's properties. The hardware persists in functioning, the physics persists in generating surprises, and somewhere between these two realities, the inquiry continues. With instruments deactivating and power diminishing, what remained discoverable depended entirely on what the final instruments could still register: the magnetometer and the plasma wave subsystem. Those are the 2 instruments that will outlast everything else on both spacecraft. They consume the least power. They have almost negligible mass, and they happen to be the 2 instruments still capable of addressing the questions that matter most. The magnetometer registers the intensity and orientation of the magnetic field. The plasma wave subsystem monitors oscillations in the charged gas surrounding the probe. Together, they can still detect the interstellar resonance, track density transitions in the medium, and chart the architecture of the magnetic field extending through interstellar space. On paper, 2 instruments sounds like the conclusion of an investigation. In practice, these 2 instruments just delivered a result that overturned one of the final, surviving predictions regarding the heliopause. For decades, theoretical frameworks assumed that the solar magnetic field and the interstellar magnetic field would point in opposing directions. That difference was supposed to represent the clearest indicator of the boundary. When Voyager 1 crossed the heliopause, the anticipated directional shift failed to materialize. Scientists debated for a year whether the crossing had even occurred. At that time, the missing reversal was characterized as an anomaly, a localized irregularity, something to be explained away. It is not a localized irregularity. With years of magnetometer data from both probes now analyzed, the picture is unambiguous. The local interstellar magnetic field exceeds 3 nanoteslas, stronger than predicted, and it aligns closely with the solar magnetic field across the heliopause. The two fields, generated by entirely different processes separated by billions of kilometers, point in nearly identical directions. Nobody predicted this. Nobody can fully explain it. 3 nanoteslas constitutes a negligible field by everyday measurements. A kitchen magnet generates a field roughly 10 million times stronger, but in the diffuse space between star systems, 3 nanoteslas carries significance. It indicates the interstellar medium exerts more magnetic pressure on the heliosphere than theoretical models assumed. And the alignment implies the boundary between solar territory and interstellar territory lacks the sharp magnetic discontinuity that 50 years of theory demanded. The boundary is magnetically continuous. That continuity is precisely why confirmation of Voyager 1's crossing required a year. The definitive signature everyone sought, the dramatic field reversal, does not exist because the fields on both sides happen to agree. Whether this alignment represents a coincidence of our local galactic vicinity or evidence of a more fundamental physical connection remains an open question. Some researchers propose that the interstellar field is draping around the heliosphere, aligning through pressure interactions at the boundary. Others argue the alignment may be specific to the local interstellar cloud, the particular region of galactic gas our solar system is currently traversing. The available data cannot yet discriminate between these possibilities. The heliosphere is not occupying a random magnetic environment. It is embedded within a field that mirrors its own. And the instrument that confirmed the interstellar crossing, the plasma wave subsystem that NASA nearly declined in 1973, continues detecting the resonance that commenced in 2017. The resonance has not ceased. The density fluctuations have not stabilized. The interstellar medium continues transmitting, and the final 2 instruments on each probe remain listening. But Voyager was never designed to chart the heliosphere from outside. It was designed to traverse through it. For a comprehensive picture, the inquiry required something entirely different. On September 24, 2025, a Falcon 9 launch vehicle lifted off carrying the Interstellar Mapping and Acceleration probe. The spacecraft arrived at the first Lagrange point on January 10, 2026, positioning itself roughly 1.5 million kilometers from Earth, where the gravitational influences of our planet and our Sun achieve balance. On February 1, 2026, primary scientific operations commenced. Following nearly 50 years of dependence on 2 probes traveling along 2 narrow paths through the heliosphere, the inquiry finally acquired a capability that could observe the complete structure simultaneously. The Interstellar Mapping and Acceleration probe carries 10 instruments with 15 to 35 times greater sensitivity than its predecessor, the Interstellar Boundary Explorer, which launched in 2008. Where the Interstellar Boundary Explorer provided scientists with an indistinct image of energetic neutral atoms streaming from the heliosphere's boundary, the new probe will generate detailed maps with sufficient resolution to track transitions across months rather than years. Energetic neutral atoms represent the essential mechanism. When charged particles from the solar wind collide with neutral atoms in the interstellar medium near the heliosphere's boundary, some of those particles capture an electron, become electrically neutral, and travel in a direct path back toward Earth. Through measuring the origin direction of these atoms, their velocities, and their species composition, scientists can reconstruct conditions at the boundary without dispatching a spacecraft there. Consider it like detecting a conflict from kilometers away by listening for acoustic evidence. You cannot observe the situation directly, but you can map what is occurring based on what reaches you. The interstellar boundary explorer had already demonstrated this technique functions. Its most consequential discovery was the ribbon, an unexpected band of energetic neutral atom emissions forming a narrow arc across the celestial sphere that no theoretical model had predicted. The ribbon appears to trace the location where the interstellar magnetic field is perpendicular to the observation line from Earth, but its precise origin remains disputed. The new probe will examine the ribbon at substantially higher resolution and across a broader energy spectrum, potentially resolving whether it originates at the heliopause, beyond it, or through some interaction bridging the two zones. But the probe's most significant contribution may be something more fundamental than resolving the ribbon mystery. It will generate the first three-dimensional maps of the heliosphere. Every conclusion derived from Voyager data carries the identical qualification. Two trajectories through a three-dimensional structure cannot reveal the shape of that structure. It is comparable to extracting two core samples through a mountain and attempting to characterize the complete mountain from those two boreholes. The probe changes this equation by collecting energetic neutral atoms from every direction simultaneously, and by monitoring how those emissions evolve as our Sun's output varies across its 11-year cycle. The mission can construct a comprehensive picture of the heliosphere's dimensions, geometry, and dynamics. The first complete sky charts are anticipated later in 2026. When they arrive, they will either confirm or contradict the competing theoretical frameworks that have been contesting each other since Voyager traversed the boundary. The Voyager probes remain out there, still measuring from within interstellar territory. The new probe observes from near Earth. For the first occasion, the inquiry possesses both a ground-level perspective and an elevated perspective of the identical structure. The question is whether the two perspectives will correspond. As of early 2026, we do not know the geometry of our own heliosphere. The comet tail model has been eliminated. Cassini eliminated it in 2017 with neutral atom data demonstrating that particles from the supposed tail direction responded to variations in solar output precisely as rapidly as particles from the forward direction. No time differential means no extended tail. 50 years of reference text illustrations depicting an elongated windsock trailing behind our solar system were incorrect. But what has replaced the tail concept has not been determined. A uniform sphere does not work either. Voyager 2 traversed the termination shock at 83.6 astronomical units. Voyager 1 traversed it at 94. That 10 astronomical unit differential, roughly 1.5 billion kilometers, demonstrates the heliosphere is being compressed asymmetrically. The interstellar magnetic field exerts greater pressure on one side than the other. In 2016, Merav Ofer and colleagues at Boston University proposed a geometry nobody had anticipated. Employing magnetohydrodynamic simulations, they argued the heliosphere might resemble a croissant, with two lobes of solar magnetic field projecting from opposing sides while the middle region contracts inward. The theoretical framework is driven by the behavior of the solar magnetic field as it rotates and folds in the outer heliosphere, generating two distinct jets of magnetized plasma. The croissant framework accounts for some observations. It explains the asymmetry between the two Voyager traversals. It accommodates certain features in the interstellar boundary explorer ribbon measurements, but it does not reconcile with everything. Other research groups have proposed forms closer to a deflated spherical object compressed on one side and bulging on the other, with the interstellar magnetic field imposing the distortion from exterior. The Interstellar Boundary Explorer revealed that the heliosphere's boundary is tilted roughly 30 degrees from the orientation theoretical models assumed, and that the tilt shifts by more than 10 astronomical units as the solar cycle progresses. The heliosphere inhales and exhales. It expands during solar maximum when our sun's output reaches its peak, and contracts during solar minimum when the wind weakens. A spherical balloon inflating and deflating by over 1 billion kilometers every 11 years. That respiratory cycle means the heliopause occupies no fixed position. It constitutes a moving target. Voyager 1 and Voyager 2 each captured a single momentary image of a boundary that shifts perpetually. The position each probe crossed communicates only where the boundary was on that specific day, in that specific direction, during that specific phase of the solar cycle. Extrapolating from those two momentary images to a permanent geometry is precisely the category of assumption that has proven incorrect at every stage of this inquiry. The interstellar mapping and acceleration probe was constructed to resolve this. Its sky charts will display the global distribution of energetic neutral atoms at varying energies, which corresponds to contrasting distances and processes at the boundary. Across time, as the solar cycle advances, those charts will reveal how the geometry evolves. Whether the heliosphere resembles a croissant, a compressed sphere, or something no one has proposed yet depends on data that does not exist until the probe delivers it. We inhabit this structure. It shields us from a substantial fraction of galactic cosmic radiation. It determines how much of the galaxy's energetic output reaches the inner planets. And, following nearly 50 years of direct exploration, we remain unable to accurately depict it. The anomalous cosmic ray problem has now persisted 22 years and counting. When Voyager 1 traversed the termination shock in December of 2004, the single most confident prediction in heliophysics collapsed. Anomalous cosmic rays, particles that originate as neutral atoms drifting into the heliosphere, become ionized by solar radiation and subsequently accelerate to immense energies, were supposed to reach peak intensity precisely at the termination shock. That constituted the complete theoretical framework. The shock was the accelerator. Voyager 1 would traverse it and register the maximum. The maximum was not present. Anomalous cosmic ray intensity did not surge at the termination shock. It persisted in rising as Voyager 1 moved deeper into the heliosheath, the turbulent zone between the shock and the heliopause. The instrument designed to detect this maximum, the cosmic ray subsystem constructed under Edward Stone's direction, registered a gradual increase with no indication of the anticipated peak. Voyager 2 confirmed the identical pattern 3 years subsequently at its own shock traversal. No maximum, merely a sustained climb. Entire research programs had been constructed on the prediction that the termination shock accelerates anomalous cosmic rays. Doctoral dissertations, computational simulation codes, funding applications. The mechanism appeared entirely logical. Neutral atoms drift inward. They become ionized. The solar wind transports them outward. They encounter the shock and rebound repeatedly across it, gaining energy with each traversal. A process designated diffusive shock acceleration. It functions for other astrophysical shock structures. It was expected to function here. It did not. The current leading hypothesis proposes that anomalous cosmic rays are not accelerated at the forward face of the heliosphere where both probes traversed. They may undergo acceleration at the flanks, the lateral surfaces of the heliosphere, where the termination shock curves away from the direction of galactic travel. At the flanks, the shock geometry differs. The magnetic field encounters it at a contrasting angle. The acceleration conditions may be more favorable there, but no spacecraft has ever visited the heliosphere's flanks. Both Voyagers traveled roughly toward the forward face. Every direct measurement of the termination shock originates from the structure's front aspect, not its sides. Envision investigating a structural fire, but being permitted only to look through the main entrance. You can characterize the entry area. You cannot describe what transpired in the interior sections. The interstellar mapping and acceleration probe may provide indirect evidence. Its energetic neutral atom detectors can register particles arriving from every direction, including the flanks. If anomalous cosmic rays are undergoing acceleration there, some portion of the resulting energetic neutral atoms should be detectable in the probe's sky charts. But indirect evidence does not equate to traveling through the region and directly measuring the particles. The acceleration origin for anomalous cosmic rays persists as one of the oldest unresolved questions in heliophysics. We know the particles exist. We register them continuously. We have tracked their intensity across 2 shock traversals and through the heliosheath and into interstellar territory. And we still cannot determine where they acquire their energy. The termination shock, the structure expected to answer this question, proved to be the incorrect answer. 22 years subsequently, the correct answer has not materialized, and the instrument that initially registered the discrepancy on Voyager 1, the cosmic ray subsystem, was deactivated in February 2025. The timeline for resolving this has contracted. If you compiled every unresolved question Voyager has generated and arranged them on a display surface, the compilation would resemble the evidence room of an investigation that keeps becoming more intricate. 7 open inquiries, none concluded, all interconnected. Begin with Pressure Front 2. Since approximately 2020, Voyager 1 has been traversing a zone of interstellar territory where plasma density exceeds the surrounding medium by 30%. This elevated density has persisted for more than 5 years. No theoretical model predicted it. No definitive explanation exists. Something in the interstellar medium is compressing the plasma along Voyager 1's trajectory, and we cannot determine what. Second, the magnetic field alignment. Solar magnetic field lines generated by our Sun, and interstellar magnetic field lines generated by galactic processes should not point in identical directions. They do. Across the heliopause, the 2 fields are closely aligned. Whether this represents a localized coincidence or indicates a more fundamental physical relationship remains unresolved. Third, the interstellar resonance. Continuous narrowband plasma emission detected since 2017. Uncorrelated with any solar event, not pulsed or periodic. A persistent low-frequency signal revealing density fluctuations across distances of 10 or more astronomical units. What sustains it, and whether it is uniform across the interstellar medium or specific to Voyager 1's trajectory, is unknown. Fourth, the anomalous cosmic ray acceleration origin. Predicted at the termination, shock, not detected there. Possibly at the flanks, unconfirmed. 22 years without resolution. Fifth, helioporosity. Voyager 2's plasma instrument detected solar particles permeating beyond the heliopause into interstellar territory. The boundary is not sealed. material migrates in both directions. How much permeates through, across what surface area, and what effect this has on the interstellar medium near our solar system all remain unresolved questions. A permeable boundary differs fundamentally from an impermeable one, and the difference carries significance for understanding how much galactic cosmic radiation reaches the inner solar system. Sixth, the geometry of the heliosphere, bubble, croissant, deflated sphere. No consensus. Two Voyager trajectories cannot resolve a three-dimensional geometry. The interstellar mapping and acceleration probe may settle this within several years, or it may reveal a geometry more complex than any current theoretical framework. Seventh, the outer heliosphere pressure imbalance. When researchers sum every known pressure contribution at the heliosphere's boundary, magnetic pressure, thermal plasma pressure, cosmic ray pressure, and ram pressure, the aggregate exceeds what theoretical frameworks predict. An unidentified component exists. Something is pressing on the boundary from outside, and the measurements confirm the pressure without identifying the source. Envision a sealed chamber where you can register the atmospheric pressure against every surface, and the readings exceed what the known air supply can account for. Pressure exists from some source, and you cannot locate it. 7 inquiries, all initiated by Voyager data, none concluded by Voyager data. The probes were never engineered to resolve these questions. They were engineered to fly past the outer planets and maintain trajectory. The fact that they survived long enough to reach interstellar territory constitutes an engineering contingency that became the most scientifically productive contingency in the history of space exploration. But productive does not equate to definitive. Every one of these 7 questions directs attention outward toward a galactic environment we have barely begun to chart. Draw back sufficiently, and the heliosphere is not suspended in empty space. It is embedded within a structure called the local interstellar cloud, a region of warm, partially ionized gas, roughly 50 light-years across. Our solar system entered this cloud at some point within the past few thousand to tens of thousands of years, and will eventually depart it. Beyond the local interstellar cloud resides a substantially larger structure, the local bubble, a cavity in the interstellar medium roughly 1,000 light-years in diameter. The local bubble was excavated by a succession of supernova detonations over the preceding 10 to 20 million years. Massive stellar bodies in the solar neighborhood depleted their fuel reserves, detonated, and the resultant shock fronts swept the surrounding gas outward, hollowing out a region of unusually low density and elevated temperature. Our solar system occupies a position near the periphery of this cavity. The elevated interstellar medium temperature that Voyager measured, 30,000 to 50,000 Kelvin, rather than the predicted 15,000 to 30,000, makes more sense in this context. The gas exterior to the heliosphere is not simply interstellar gas. It is gas that has been thermally processed by stellar detonations that transpired millions of years before our species came into existence. The density fluctuations generating the interstellar resonance, the pressure anomalies nobody can account for, the magnetic field structures failing to correspond with simplified theoretical models. All of it may represent the enduring residual signature of extinct stars. Consider the magnitude. A supernova releases roughly as much energy in a matter of seconds as our Sun will generate across its entire 10 billion-year operational lifespan. That energy does not simply dissipate. It propagates through the interstellar medium as compression fronts, thermally elevates the surrounding gas, compresses magnetic field configurations, and generates turbulence persisting for millions of years. The Kolmogorov spectrum turbulence that Voyager 1 detects in the interstellar resonance, density variations adhering to a specific mathematical pattern at astronomical unit scales, is consistent with turbulence initiated by ancient energetic events and sustained by the continuing dynamics of the interstellar medium. Voyager is registering the cosmic meteorology, and that meteorology was set in motion by detonations predating human civilization by a factor of 1,000. This is not abstract cosmological speculation. The local bubble influences us directly. The density of the interstellar medium exterior to the heliosphere determines how much pressure is directed inward on the boundary. If our solar system occupied a denser galactic region, the heliosphere would be smaller. The termination shock would be positioned nearer. More galactic cosmic radiation would reach the inner planetary system. The heliosphere's dimensions are partly determined by our Sun's output and partly by the external environment. That environment is configured by supernova activity. Some researchers have speculated that historical passages through denser interstellar zones may have temporarily contracted the heliosphere sufficiently to alter the cosmic ray flux reaching Earth, potentially influencing atmospheric chemistry and climate across geological timeframes. This remains speculative, but it is not unreasonable. We know the heliosphere changes dimensions. We know it responds to external pressure, and we know the interstellar medium is non-uniform. What Voyager detected at the solar system's boundary is not merely the solar system's boundary. It is the frontier between our Sun's sphere of influence and the accumulated consequences of every energetic event in our galactic neighborhood across the preceding 20 million years. Something fails to reconcile regarding the two heliopause traversals, and it extends beyond differences in plasma measurements and boundary thickness. Voyager 1 crossed at 121.6 astronomical units in August of 2012. Voyager 2 crossed at roughly 119 astronomical units in November of 2018, 6 years apart, contrasting trajectories through the heliosphere, contrasting phases of the solar cycle. Voyager 1 crossed during a period approaching solar maximum. Voyager 2 crossed closer to solar minimum when the solar wind is weaker and the heliosphere should be more contracted. A weaker solar wind produces less outward pressure, which means the boundary should contract inward. Voyager 2 should have traversed the heliopause substantially nearer than Voyager 1. It did cross nearer, but by only approximately 2.5 astronomical units, roughly 375 million kilometers. Given the difference in solar, wind conditions and the contrasting trajectories through the heliosphere, theoretical models predicted a substantially larger differential. The similarity in traversal distance was nearly as surprising as the differences in what each probe registered at the boundary. For decades, the heliosphere's scale was characterized primarily as a function of solar output. More intense solar wind extends the boundary outward. Weaker outflow permits contraction. The 11-year solar cycle should pump the heliopause in and out by 10 astronomical units or more. This model is not entirely incorrect. The heliosphere does respond to solar wind variations, but Voyager's data demonstrated that the external environment carries equal weight. The interstellar medium is not a passive backdrop. It resists. The local interstellar magnetic field, measured at more than 3 nanoteslas, exerts continuous pressure on the heliosphere from outside. The thermal pressure of the elevated temperature interstellar plasma contributes to it. The ram pressure of the interstellar medium flowing past the heliosphere adds further. The boundary is not established by our sun alone. It is a negotiated equilibrium. Consider it like a soap bubble suspended in a breeze. The internal air pressure establishes the tendency to expand, but the external wind determines the actual geometry and position. If the wind remains steady, the bubble maintains roughly the same scale regardless of minor variations in internal pressure. The interstellar medium surrounding our solar system constitutes that wind, and it is not inconsequential. This transforms how we conceptualize the heliosphere's stability. If external interstellar pressure carries equal importance to internal solar wind pressure, then the heliosphere's dimensions and geometry depend as much on galactic conditions as on solar conditions. Our solar system moves through the galaxy at roughly 84,000 kilometers per hour. The local interstellar cloud it currently traverses is non-uniform. Density varies. Magnetic field intensity varies as the solar system enters regions of contrasting interstellar properties. The heliosphere will respond. It could contract. It could reconfigure. It could, in principle, be compressed sufficiently to expose the inner planetary system to substantially elevated levels of galactic cosmic radiation. None of this is imminent. The current interstellar environment appears relatively stable across human time frames. But across astronomical time frames, the heliosphere is not a permanent shield. It constitutes a temporary arrangement between a stellar body and the galaxy it traverses. Voyager demonstrated that the galaxy's contribution to this arrangement is more substantial than anyone anticipated. 2 probes, 2 trajectories through a structure extending in every direction. This constitutes the fundamental constraint on everything Voyager has communicated about the heliosphere, and it merits explicit acknowledgement. Voyager 1 traveled roughly in the direction the heliosphere faces as it moves through the interstellar medium, the designated nose direction. Voyager 2 traveled at a contrasting angle roughly toward the heliosphere's southern hemisphere. Neither probe sampled the flanks. Neither sampled the polar regions. Neither approached anywhere near the zone where the tail was expected to be. Every characterization of the heliosphere's 3-dimensional geometry, based on Voyager data, constitutes an extrapolation from 2 linear trajectories through a volume spanning hundreds of astronomical units in every direction. The interstellar mapping and acceleration probe will provide a 2-dimensional celestial chart of the heliosphere, reducing the 3-dimensional structure to a projection comparable to a flat representation of Earth's surface. This represents a substantial improvement over 2 trajectories. But a 2-dimensional projection still cannot unambiguously reconstruct 3-dimensional geometry. Obtaining the genuine form requires either multiple contrasting vantage points or measurements encoding depth information. The probe's temporal series data, monitoring heliosphere variations across a complete solar cycle, may partially substitute for multiple vantage points. As the heliosphere contracts and expands, contrasting zones shift in and out, and the resulting variations in energetic neutral atom flux can reveal information about the 3rd dimension. It constitutes an indirect method possessing inherent limitations. The most direct approach to resolving the open questions would involve dispatching a spacecraft to 1,000 astronomical units, sufficient distance to observe the complete heliosphere in galactic context. This represents the interstellar probe concept that NASA and the Johns Hopkins Applied Physics Laboratory have studied for years. It would carry contemporary instruments along a trajectory designed to complement Voyager's paths, sampling the flanks, or the tail region, the zones where anomalous cosmic rays might actually undergo acceleration, where the heliosphere's geometry is most uncertain. The concept remains without allocated funding. No mission is under active development. No launch date has been proposed. With existing propulsion capabilities, reaching 1,000 astronomical units would require multiple decades. The fastest outbound spacecraft ever launched, New Horizons, travels at roughly 58,000 kilometers per hour relative to our Sun. At that velocity, 1,000 astronomical units represents more than 40 years of travel time. Voyager 1, traveling at roughly 61,000 kilometers per hour, will reach 200 astronomical units sometime in the late 2030s. That still amounts to less than 1/5 the distance to the proposed interstellar probe destination. In the interim, we have what we have. 2 aging probes registering localized conditions along 2 trajectories. 1 new probe registering global emissions from near Earth, and decades of data contradicting nearly every prediction formulated before the measurements existed. The heliosphere represents the only astrophysical structure we inhabit and can study from both the interior and the boundary simultaneously. No other stellar system affords us that opportunity. But the opportunity is constrained. It depends on instruments losing generating capacity and a follow-on mission that has not received funding. We are mapping a continent from 2 footsteps and an aerial photograph captured from 1,000,000 kilometers distant. The continent is genuine. The footsteps are genuine, but the chart between them remains largely blank. The power budget on Voyager 1 shows approximately 227 watts available from the radioisotope thermoelectric generators as of early 2026. Voyager 2 is comparable. The plutonium-238 within each generator undergoes decay at a fixed rate, and nothing can alter that. 4 watts less annually. 4 watts is not substantial. A typical ambient lamp consumes about 4 watts. But aboard a spacecraft where every instrument, every thermal system, every processing cycle operates on a total power budget smaller than a standard incandescent lamp, 4 watts annually represents a countdown. The cosmic ray subsystem on Voyager 1 was deactivated in February 2025. Edward Stone's instrument, the one that identified the anomalous cosmic ray discrepancy at the termination shock in 2004, ceased operation. On Voyager 2, the low-energy charged particles instrument constructed under Tom Crimigas was deactivated in March 2025. Crimigas is the sole scientist in history to have built instruments that traveled to all 8 planets. His detector on Voyager 2 no longer transmits data. The plasma science instrument on Voyager 2, the one John Richardson's team at MIT employed to make the sole direct plasma measurement at the heliopause, was already deactivated in September 2024. Every one of these deactivations is irreversible. No instrument can be reactivated once the power has been reallocated. The determination of which instrument to deactivate is made by Suzanne Dodd's team at the Jet Propulsion Laboratory, and it is made based on which remaining instruments can generate the most scientifically significant data per watt consumed. By the conclusion of 2026, each probe will likely retain 2 or 3 active instruments. The magnetometer and plasma wave subsystem are expected to be the final operational instruments on both spacecraft. They consume the least power, and they provide the data most relevant to the open questions, magnetic field measurements, and plasma density via wave detection. If the power decline continues at its current trajectory, these instruments may remain operational into the early 2030s. After that, insufficient power will remain to operate any scientific instrument whatsoever. The spacecraft may continue transmitting a carrier signal for several additional years, a radio tone confirming their continued existence, but conveying no data. Then even that will cease. No other spacecraft is directed toward the heliosphere's boundary. New Horizons, which passed Pluto in 2015, follows a trajectory that will carry it into the outer solar system, but it is not expected to reach the heliopause before its own power budget is exhausted. No funded successor mission exists that will traverse the termination shock, cross the heliosheath, or sample the heliopause. When Voyager falls silent, direct measurement of the heliosphere's boundary concludes. The interstellar mapping and acceleration probe will continue its observations from near Earth. But 1.5 million kilometers is not 24 billion kilometers. Remote sensing and in situ measurement address different scientific questions. We are in the final years of a capability requiring 50 years to achieve, and for which we have no replacement plan. Every month that the magnetometer and plasma wave subsystem continue operating, they register measurements from a region of space no other instrument can access. That data may represent the final measurements of its kind for decades, possibly longer. The central question was specific. Why does nothing at the boundary of our solar system correspond to what we predicted? The termination shock was 14 astronomical units nearer than theoretical frameworks indicated. The anomalous cosmic rays did not reach their maximum where expected. The heliosheath was not smooth, but populated with magnetic bubbles the diameter of the Earth-to-Sun separation. The heliopause was 20% nearer than predicted, and when Voyager 1 traversed it, the magnetic field barely shifted direction, leaving scientists incapable of confirming the crossing for over a year. The interstellar medium turned out to be 30,000 to 50,000 Kelvin, nearly double the predicted temperature, yet so rarefied that a human would perish from cold within it. The heliosphere carries no tail. Its geometry is unresolved. Its boundary permits leakage, and a persistent resonance vibrates through what was expected to be silent, empty space. Two spacecraft traversed the identical boundary and described contrasting phenomena. The magnetic fields on both sides of the heliopause are aligned for reasons nobody can explain. An unidentified pressure contribution acts on the heliosphere from outside. Plasma density along Voyager 1's trajectory has exceeded normal levels by 30% for 5 years, with no identified origin. The source of anomalous cosmic ray acceleration predicted at the termination shock has been absent for 22 years of investigation. The question is not resolved. It has expanded. What commenced as an inquiry into the solar system's boundary became an inquiry into the relationship between our Sun and the galaxy. The heliosphere is not a permanent shield erected by the solar wind. It constitutes a negotiated boundary configured equally by internal pressure and external force. Contracting and expanding with the solar cycle, responding to interstellar conditions evolving as the solar system traverses the galaxy at 84,000 kilometers per hour. The local interstellar cloud, the local bubble, the magnetic field architectures deposited by supernovae detonating 10 million years ago. All of these exert inward pressure and configure the bubble we inhabit. Right now, Voyager 1 is positioned roughly 165 astronomical units from Earth, transmitting data at the velocity of light that requires more than 22 hours to arrive. Voyager 2 is approximately 140 astronomical units out on a contrasting heading, registering a different sector of interstellar space. The magnetometers on both probes are still recording. The plasma wave subsystems are still listening. The interstellar resonance persists. The interstellar mapping and acceleration probe has commenced scanning the complete celestial sphere from its position near Earth, constructing the comprehensive charts that will either validate or overturn the theoretical frameworks that remain. Its initial complete results will arrive within the year. When they do, they will describe a heliosphere that two probes spent 50 years traversing, and that we still cannot accurately represent on a display surface. The inquiry is not concluding. It is accelerating. The instruments are deteriorating, but the questions are multiplying at a pace exceeding the power decline. Every year of new data from both the probes and the mapping mission will either sharpen the contradictions or begin to resolve them. Either outcome transforms what we believe we understand about the space between star systems. And somewhere past 165 astronomical units in plasma, thermally elevated by extinct stars, transmitted on a signal requiring nearly a complete day to reach Earth. Two machines built by human hands in the 1970s, operating on less power than a household lamp, are at this moment the farthest reaching objects our species has ever placed in the universe. They were not designed for this. Nobody planned for them to still be working. Nobody drew up a mission profile that ended with a probe sending data from beyond the solar system nearly half a century after launch. And yet here we are, still listening, still learning, still revising every assumption we held about the space surrounding our own star. That is the quiet miracle underneath all the science. Not that we built something that reached interstellar space, but that we built something honest enough to tell us how wrong we were when it got there. The questions Voyager leaves open are not failures. They are invitations. Every unresolved anomaly, every pressure imbalance, every density gradient that should not exist, represents a direction we have not yet traveled, and a discovery waiting at the end of it. The heliosphere is not a solved problem. It is the frontier. And the frontier, as Voyager has shown us, is always stranger and richer than anything we imagined before we arrived.